Solving exponential and logarithmic equations. Now that we know that a logarithm is the inverse of an exponential function with the same base, we can use that to either solve exponential equations or solve logarithmic equations. All right, so if we're given two functions such as these, f of x is equal to b to the x power and g of x is equal to log base b of x, these would be inverses of each other. If we were to build composites of them, we would actually get the result of x. Okay, inverse functions will undo what the other one does. All right, so if you build a composite with them, you will get back your input. Okay, but the really important thing here is to get an idea of what it looks like when you actually build the composites of these. Okay, g of f of x. What that means is we're going to take the g function and input the f function into it. Okay, so b of x is going to replace this x here. We're going to get log base b of b to the x power. Okay, we are just substituting in this function, b to the x power, in for that x, and it looks like this. Okay, and now what we already know about inverse functions is that as composites, you're going to get back your input. It's going to simplify down to x. So what we want to realize here is that all of this information, if you have log base b of b to a power, you're going to end up just getting back that power. Okay, so you're going to want to see in some problems a little bit later on, and you're also going to want to force certain problems to do this, that you have a log base b of b to some power. That'll eliminate the log, and it'll also eliminate the base. You get back just that exponent. All right, so then the other composition, f of g of x, we're going to place this into the exponent position. We're going to get b to the log base b of x. And again, if you build a composite with inverse functions, you're just going to get back your input. So visually, you want to pick up on this. If you have a base raised to the log of the same base, all of that's going to cancel out and just give you back what we have here. All right, let's take a look at example 1. We want to simplify these expressions, which are going to end up just being compositions of exponentials and logarithms. What we have here is 10 to the log of 4. Okay, now you don't see the base here because that would be the common logarithm, but there is that little 10. There would be that little 10. The common logarithm is base 10. So this structure, though it doesn't look exactly the same because of the way that I wrote that 10, is going to fit what we have here. This value, this b, is the same b that we have here. We've got the 10, we've also got the 10 there. Okay, so all of this is going to cancel out and just give us back 4. Which we can verify in a calculator. We're going to take 10 and raise it to log base 10 of 4. And we get back 4, which we could also type this as 10, just raise it to the log of 4. Okay, same thing because that would be base 10. All right, for the second, we have log base 5 of 25 to the x power. Okay, now this does not quite fit the structures that we see here, but it best starts to match this one here. We've got log base 5. What we don't actually have, though, is a 5 right there. We actually have a 25. However, 25 is just equal to 5 squared. So 25 to the x power is going to be equal to 5 to the 2x power. Okay, so then we could rewrite this as log base 5 of 5 to the 2x, which is going to simplify down to just 2x. For examples 2 and 3, we're going to be solving equations by using the inverses of logarithms and exponentials, which of course are the inverses of each other. For example 2, we're going to be looking at 4 to the x power is equal to 11. And what we're going to do is take the logarithm of both sides here so that we can get that x out of the exponent position. Okay, now this is 4 as a base, right? This is base 4 raised to the x power. What we're going to do is use the logarithm with the base of 4. So if we take log base 4 of both sides of the equation, we're going to be able to get that x by itself. Okay, log base 4 of the left side is going to be equal to log base 4 of 11. Okay, and now what we've done here is we've set it up so that we get a composite of inverse functions, which is going to simplify down to just x. So we get that x is going to be equal to log base 4 of 11, which this is something that we could input into a calculator. All right, so we can take log base 4 of 11 and get back about 1.73. Okay, and just to verify that that looks good, let's go ahead and take 4 and raise it to that power. So instead of rounding off, we'll just recall it. And we get back 11, which means that this is the solution. For example 3, we're going to start with a logarithm. So what we're going to be doing is using an exponential to help solve for the x that is inside of that logarithm. In particular, what we have here is the natural logarithm, which has a base of e. So what we're going to do is make both sides of the equation an exponent to the base of e. Okay, we're going to write this as e to the natural log of x plus 2 is equal to e to the 6th power. We made both of them the exponent to the same base. Okay, now over here what we would have is e log base e of something. Okay, so all of this is going to cancel and just give you back the x plus 2, which will be equal to e to the 6th power. Then to get x by itself, we would just subtract 2. And this is the answer to x, which we'll just go ahead and evaluate into the calculator. All right, we're going to take e and raise it to the 6th power, which you usually have a button for that. Okay, so we got e, we're going to input a 6 into the exponent. We're going to then subtract 2, which is going to give us 401.4. All right, we're going to go ahead and verify that that does work here. Okay, so we can take the natural log of our answer plus 2 and see that it comes back to be 6. All right, a little note here. Notice that examples 2 and 3 can also be solved by rewriting them. Okay, now these are techniques that you can use on a regular basis, and you do want to use them for certain problems. Okay, but in some cases, you can also solve these by just converting between logarithms and exponentials, which is something unique that we can do with these inverse functions. Okay, so for example 2, what we could have done, okay, going back to the original, we got 4x, well, 4 to the x power is equal to 11. We can do the old switch here. We're going to write this as log base 4, switch these, you're going to get 11 is equal to x, which this is exactly the same thing as what we got there. Okay, so both methods work. This may appear to be a little bit easier, but there are practical uses for this. All right, for example 3, we can basically do the same thing. Remember that this is log base e, right? This is log base e. So we can just keep the e, switch these two parts around, we get e to the 6th power is going to be equal to x plus 2, which looks exactly like this. Okay, so then e to the 6th minus 2 is equal to x, which is exactly what we had here as well. Okay, so again, this might appear to be a little bit easier than the method used here, but there are practical uses for being able to do this. All right, for examples 4 and 5, we're going to go ahead and use that converting method to solve here. Example 4, we have log base 5 of this is equal to 3. We'll go ahead and just switch things around. We'll drop out the logarithm. We're going to write this as 5 to the 3rd power is going to be equal to 5x minus 1. Okay, 5 to the 3rd power is 125. We got 125, and what we're going to end up doing after that is adding a 1 over. So let's just go ahead and call it 126 is equal to 5x. Go ahead and divide by 5. 126 divided by 5 is going to be 25.2. Which we can also verify in the calculator. We'll just get log base 5 in there. We've got 5. I'm going to recall the last answer. subtract 1, and we get 3. In example 5, we've got x in 2 different locations, which happen to be in 2 different logarithms. However, the bases of those logarithms are going to be the same thing. They're both base 10. This is that common logarithm. Okay, so what we're going to start off with here is one of our logarithmic properties. We're going to go ahead and blend these together using what is called the product rule. We'll just need to multiply the 8x by the x minus 20. So we're going to get log of 8x multiplied by x minus 20, and that would be equal to 3. All right, now I'm going to go ahead and take care of a couple things here. One, we've got a base of 10, so we can go ahead and do a little bit of a switch. We can write this as 10 to the 3rd power and set that equal to all of this. Okay, but what I'm going to do is go ahead and multiply that through. So that's going to give us 8x squared minus 160x. Okay, so take care of a couple things there. All right, now what we've got is a quadratic. Okay, we've got x to the 2nd power. Okay, so I'm going to move everything over to one side, make that a 0. This is actually 1,000. Okay, so we'll subtract that. All right, so we have some large numbers here, but the good news is that everything's divisible by 8. Of course, these two will be divisible by 8 because that's how we built them. But 1,000 is also divisible by 8. Okay, so let's go ahead and divide that out. That's going to get us down to an x squared minus 20x minus, let's go ahead and check this one out. We have 1,000 divided by 8, which is 125. All right, so the only factors of 125 are going to be 5, 5, and 5. So all we really need to do is think about how can we use those numbers to get a product of 125. That also gives us a difference, actually a product of negative 125. That also gives us a difference of 20. And that combination is going to be 25 and 5. If 25 is negative and 5 is positive, we'll get the correct product. We'll also get the correct difference as a negative. Okay, so this is going to factor into x minus 25 times x plus 5. Again, their product is negative 125. Their sum is going to be negative 20. Okay, so from here, the solutions that we would get would be 25 and negative 5. But going back to the beginning where we have a logarithm, you can actually have an input that's negative. So if we use the negative 5 here, or even here, we're going to be plugging negatives into logarithms, which just doesn't work. So the one answer we're going to keep is going to be the 125. All right, let's go ahead and test that out just to see that it does work. We're going to take log of 8 times 25 plus log of 25 minus 20, and we should get back 3, which we do. For example 6, I have an alternative method for solving for an exponent, which I refer to as cool trick number 6. All right, so we've already solved this before, and we know the answer to it, which was 1.73. Okay, what I'm going to do here for cool trick number 6, I'm going to take the natural logarithm of both sides. Okay, so I'm going to write this as the natural log of 4 to the x power is going to be equal to the natural log of 11. Okay, balancing method, everything is fair. And then what I'm going to do is use the quotient rule, which is going to allow me to take this exponent and move it out to the front. So I get x multiplied by the natural log of 4 is equal to the natural log of 11. Then to solve for x, I can actually divide by the natural log of 4. And believe it or not, this is going to be 1.73. And there you go. Cool trick number 6.
Wait, there was.